7.1 definition of the Laplace transform. So from what I mentioned earlier, the one that you saw in the chapter 4 and chapter 5, the mass spring problems and also the electrical circuits. For the equation that we are familiar with, I'm sure you are familiar with, like mx double prime plus beta x prime plus kx plus f of t. The m like the mass multiplied by the acceleration due to the gravity, and then the beta, that is the damping constant. That's from the that that term, the beta x prime is the damping force that's affected by the surrounding or the media. The kx, that's from the spring. K is the spring constant. The capital Ft, that is the external force. If F is 0, so we have the homogeneous. That means no other force effect to the system. That's the simple case, or the case that we don't have to find Yp or the particular solution. And for the electrical circuit, the E as the source of the voltage, the L, that's from the conductor, and Ri from the resistor, and 1 over C times Q, that's from the capacitor. So it could be 2 or 3 or all three of them, but the relationship, the I and the Q, I is the dq dt and so forth. And the E here, the source of the voltage, that is um, it could be the function as a trig function or the on off or the switch problem that I mentioned earlier. So the case that the E or the F is discontinuous, so then the previous method is not quite convenient to solve it. So that's why Laplace transform is another tool to work on those kind of problems. Okay, we are talking about the transformation. So involving the transformation, this time in the past, the transformation that we touched a little bit, that would be the operator D. I'm gonna go down here real quick. The operator D, like when you solve the system, remember we rewrite the derivative like x prime as dx, the y prime as dy, and the x double prime as d square y, d square x, and so forth. So operator D is the operator that we can apply to the function and make it as a derivative. But for the Laplace transform, is the opposite process. The detail is not the same, but the idea of it is transformed into the new function of the f, but using the integration, not using the derivative. Kind of the another path in calculus that you can see it is as a use. Um, so operator D in the derivative way and the Laplace transform in the integration way. So for the Laplace transform, the definition, we use the script L, or you can just recall the Laplace of the function f of t is this is an improper integral. As you see, the integral from 0 to infinity, e to the negative st multiplied by the function ft. The ft is the function that you're going to apply the Laplace transform to. So basically changing from the function of the t into the function of the s using the integral method. Okay, and this is the improper integral, so the limit will be involved to find the solution of this integral. And the term, the e to the st, this is called the kernel, or the kind of um, like the process to transform. When you have the machine, you have the input is fed into the machine process it, and the integral, the e to the s negative st, is kind of the mechanic inside of the machine that process it and then get it out as the new function in the form of the independent s variable. Okay, so at the beginning, we're going to use a definition. That means we're going to use an improper integral to find the Laplace transform of the function of the t. The function of the t could be any function form, could be the constant, polynomial, exponential, the hyperbolic function, any kind of the function, as long as you can find the improper integral using the kernel e to the negative st multiplied by that function, and comes out as another function of the variable s. Okay, this one is called the definition of the Laplace transform. So the homework this week we skip the homework because I will put 7172 homework together with the rest of the chapter 7 as one single homework. And the question will ask you to use the definition. That means you have to show the work using the improper integral. So by the definition, use the integral from 0 to infinity of the kernel e to the negative st times ft and so forth. Okay. If it doesn't say like use the definition, you can apply the theorem, which is very convenient that we're going to see later on. Okay. For the behavior of the function fs, which is the Laplace transform of the function f of t as s approaches infinity. In the case that the function f to begin with, the original function is a piecewise continuous on like starting from 0 to infinity, but the application, most of it is about the circuits. So the time is the independent variable, so the time will be greater than or equal to 0. So that's why the lower limit is starting at 0, and the upper limit, it could be open end or like it approaches to infinity. And the exponential order, that's pretty much the part of the e to the negative st. So in general, we can say that if f is a piecewise continuous function, and then the limit of this function as t approaches infinity going to be 0. Or if you recall, it's about the transient term, the steady state. The transient term, the limit will approach 0 as t approaches infinity. Well, we'll see when we get to some of the examples. I'll explain more. Okay. And the overall picture of the use of the Laplace transform, it will convert the differential equation in the function of t into the algebraic equation in the function, the capital F of s, from t to s. Okay. All right. Let's get to the first example. Let me make some room here. So for the first one, the function f of t is 1, and by definition, I'm going to write the definition for the Laplace transform. Oops, I have to change the color. Oops. So the Laplace transform, or we just use the script L of the function as a function of the t, is the improper integral from 0 to infinity e to the negative st multiplied by the function, original function at t. Okay, and with respect to t. For the integral, the t is the independent variable. So for number 1, the function ft is 1. So the Laplace transform of the ft, which is the Laplace transform of the 1, is the improper integral from 0 to infinity e to the negative st multiplied by 1 with respect to t, or just the the integrand is just e to the negative st with respect to t. And since this is the improper integral, we apply the limit at the end point or the upper limit. So we use the notation b. So limit as b approaches infinity of this integral. Now we are treating it as the limit of the definite integral. Okay, as you recall, this is what you did in Calc 2 toward the end of the the chapter 7 about the technique of integration. So from this is not too bad since the integrand is e to the negative st. So the antiderivative is just e to the negative st. Recall the t is the independent variable. We treat s as the constant. Okay, since you are doing with respect to t, so the antiderivative is e to the negative st divided by negative s. So I put negative over here and s right here, and take the limit as b approaches infinity. Evaluate from the lower limit 0 to the upper limit b. Same routine as what you did um, for the for for finding the indefinite integral. And now, since the limit is involved, so we have to be careful. Negative side, I take it out, treat it as the common factor. So take the limit as b approaches infinity. For the upper limit, e to the negative s b, because this is about a t, right? So this is t value, this another t value. Wherever you see t, you just replace by lower and upper limit and subtract them, divided by s, and then subtracted by e to the power negative s multiplied by 0, divided by s. And as you see, b approaches infinity. This term will approach 0 because the negative power of the e is the reciprocal. So as it divided by very large quantity, the whole quotient will approach 0. And then it leaves us just the last term. We have the negative side, and the negative side here, it becomes positive, and e to the power 0 is 1. So the answer is 1 over s. So now this is one of the formula that you're going to see, or part of the theorem. The Laplace transform of the constant is 1 over s.